of degree d, which make a space of dimension d minus 1. But for simplicity of exposition, I will talk about degree 3 polynomials with marked critical points. And study, so I want to study questions about the distribution and about special points in this space. Alors, so I said yesterday that this space, so let's say we call it P3 with marked critical points. It is essentially isomorphic to C2. And it is very useful, it is important in this kind of problems to find efficient parameterization of this space. So first tentative is to parameterize it like this. With two parameters A and B. And if you try to look for critical points, if you look for critical points here, you get an equation which is 3z squared plus a equals 0. You cannot mark them. So the first tentative would be to do this. So you put a square here, and then indeed you can mark critical points at plus a over 3 and minus a over 3. So actually it's not the best choice. So we will choose another parameterization. So we actually use the following parameterization, a parameterization where the critical points are marked at respectively 0 and C. So you can choose, again, you can play with the affine conjugacy, so you can choose where you want to put critical points. And I will put them at 0 and C. This one will be C0, and this one will be C1. And so it means that the derivative of my polynomial, I choose it to be z minus c. Okay, and then I just have to integrate to find the value for p. So my parameterization would be p, so that there will be two parameters. One is this parameter c, another one which is parameter a. It is z cubed over 3 minus c z squared over 2. I have one free parameter of integration. So I can put an a here. Actually, for technical reasons, it is better to put a cube here. So this will be my parameterization. Okay, so it looks a little bit complicated, but for various reasons, it is reasonable. But again, what is important, besides this explicit formula, is to know that you have a space of polynomials, which is of dimension 2, and you have two critical points, which you can follow holomorphically everywhere. Okay, and so you have two critical points, C0 equals 0, and C1 equals C. Okay, so as I said yesterday, special points here, special points in this space are post-critically finite parameters. Meaning that both critical points have finite orbit. Are pre-periodic. And in this setting, so you can ask question of André Hort type. So you can ask many questions. What is the distribution of this of these special points? So how are they distributed? Are they Zariski dense? And do they equidistribute to some measure? And also, can you describe, so I will say in a moment that they are Zariski dense. Can you describe special curves? So can we describe curves going through infinitely many of these special points? So these are my goals for the moment. Okay, so let me state. So just a comment, if you want to go to higher dimension, you can do exactly the same. You can mark d minus 1 critical points. One will be 0, and you have d minus 2 parameters. You make the same calculation with a more complicated formula, and you put a to the d at the end. You get a parameterization of critically marked polynomials of degree d. Okay, so first proposition. So the set of post-critically finite parameters is countable and Zariski dense. And also it is bounded in the usual topology. It is bounded in situ. Okay, so how do you prove this? So, okay, so proof. So, as I said, a parameter is post-critically finite. So PCA belongs to the set of post-critically finite parameters if you have two equations of the form P CA of n naught of C naught equals PCA m naught of C naught for some, say, n naught bigger than m naught, and the same for C1. Okay, so they are defined by equations with coefficients in Q. Notice that this is a so these are algebraic equations over Q. So if you want to show that this is countable, you just need to show that it has no component of degree 1, of a dimension 1. Okay? And so you introduce, so recall that PCA has a green function, G of CA, which is the limit. So it is in dynamical plane as n goes to infinity, 1 over 3 to the n log plus of PCA iterated n times of z. And exactly as in the quadratic case, you get functions in parameter space by plugging C here. So you define two functions, and so define G naught, it is GCA of, so it's a function of CA at C naught, and G1 of CA, GCA of C1. So you can plug the critical points in the green function, you get to get function defined on parameter space. And GCA is the max of G naught and G1. Okay, so remember for the quadratic family, this GC of C was the green function of the Mandelbrot set. So here it's this G here is a kind of green function of the corresponding set in two dimensions. And so you can make estimates. So you can, working with the polynomials, it's not completely obvious, but you can estimate these functions. And actually, there's this theorem, maybe proposition, by Brunner and Hubbard, which gives, in this parameterization, an estimate of the green function of this G as CA goes to infinity. So actually, GCA is equivalent to the log of the max of modulus of C modulus of A plus an O of 1 when CA goes to infinity. Okay, so when you go to infinity, G goes to infinity at a certain rate. So it implies in particular directly that the set of post-critically finite parameters is bounded, because for for a post-critically finite parameter, the function g is equal to 0. So from this you get that the set of post-critically finite maps is bounded. And you also get that there is no one-dimensional. So, of course, an algebraic subvariety of C2 of positive dimension is unbounded. So it implies that none of these equations has a codimension 1 component. So also that it is of dimension 0. So all equations written there of this form star have finitely many solutions. Have finitely many solutions. Okay, so it is a set of dimension 0, a countable set. Okay, and last thing I have to prove is Zariski density. And to prove this Zariski density, there is a result which is useful, which I will use several times. And which I will not prove. So it's a theorem which was proved by actually by myself and Favre, and with input from Macmillan. And the proof it's a general statement. So remember the definition of active and passive critical points. Critical points. So passive, so for you take a holomorphic family of rational maps with a marked critical points, and an active critical point is the one which is bifurcating. So active at lambda naught is equivalent to say that for every neighborhood, the sequence of iterates of C is not a normal family. And passive is the opposite. Okay, so active means bifurcating for a critical point, for a single critical point, and passive means non-bifurcating. And the theorem is like this. So let f lambda c lambda be a holomorphic family of rational maps of degree D with a marked critical point, and I will assume that it is parametrized by an algebraic parameter space, parametrized with a quasi-projective parameter space lambda. So you assume that you have an algebraic family of actually, it's an algebraic family. It's not important. With a quasi-projective parameter space, you assume that C is passive everywhere. Okay, so you have an algebraic family of rational maps, and with a critical point which is passive throughout the family. Then actually you can classify completely what happens. Then you have two options. Either the family is isotrivial, isotrivial means that all the mappings are conjugate by Möbius transformations. So the f lambda are conjugate by Möbius transformations. Or the second possibility is that the critical point is periodic throughout the family. It's pre-periodic on the family. So there exists some k such that fn of C is equal to fk of C throughout the family. Okay, so this is the only possibility for a critical point to be passive on an algebraic parameter space. So you have to, somehow it is connected with these ideas of Montel Theorem and all that, on a big, on a sufficiently large manifold, being a normal family is very restrictive. Think about the Montel Theorem. But it's not easy. So I don't explain how you prove this. So it's okay. I don't want to explain how we prove this. It's not an easy result. Then let me back to Zariski density. Of post-critically finite parameters. So what you have to prove is the following. You take a Zariski's closed set. So let X in C2, a curve. And you want to show that, so let me call C this curve, there exists a PCF parameter outside C. Okay? So what you do is you consider the family PCA parameterized by CA in C2 minus the curve. So that's a quasi-projective family of polynomials. So by this result here, and of course it is not isotrivial because the parameterization of our critically marked polynomials is essentially injective. Okay, so it's not isotrivial, so it's quasi-projective and not isotrivial. So you have two options. Either the point C is active, so either the parameter is active somewhere, and look at, say, the first critical point C naught. And so you have two possibilities. Either C naught is active somewhere, or it is passive everywhere, and it is persistently preperiodic. So in any case, and remember that when the point is active, you can always make a small perturbation to make it preperiodic, because of the Montel Theorem. This is something I explained yesterday. So in any case, you can find any case meaning active or passive, we can find a parameter lambda, CA, such that PCA of C naught, so C naught is preperiodic, and not M naught of C naught. Okay? Now you will make an inductive procedure. So here it's easy because we have only two dimensions. Now you look at the variety which is defined by this equation. So now look at the variety in C2 curve defined by this equation. No, M naught of C naught. Let's call it lambda. Again, it is quasi-projective. Maybe it's all of C2 minus C, but in any case, it is quasi-projective. And applying the same reasoning for C1. And apply the same reasoning for C1. So you are inside this variety, and then you find a new parameter where C1 is preperiodic. Okay, and this finishes the proof. Get C1 preperiodic. Okay? So this set of post-critically finite parameters, so it's not very easy to visualize. You're in C2. You are in C2. It's a countable set of points which is bounded. And actually, the closure of this countable set of points is contains the connectedness locus. So remember, the Mandelbrot set is the set of parameters where quadratic Julia set as is connected. Okay? So here you have the same kind of phenomenon. The closure of this countable set of points is the set of parameters where the Julia set is connected to. Okay, so next item. Next item, post-critically finite maps are equidistributed. Of parameters. Okay, so we will make the same reasoning as in the quadratic case. So we have a function GCA, which is the max of GCA of C naught and GCA of C1 at the Archimedean place. Okay. As in the quadratic case, I can do exactly the same kind of construction at the p-adic places too. So we can make same construction at non-Archimedean places. Okay, so you define, I explained that you can define the green function. So G CA of Z is the limit 1/3 to the n log plus of PCA n of Z. But now it's the p-adic norm. And again, you can plug C0 and C1 inside, and to get GP of C, let's say G0P of CA, which is, so I should put a P somewhere, P here, GCAP of C0, and the same for C1. GCA P of C1. So you can redo these calculations, and in particular, you get the same estimate on the growth at infinity, which is still here. So the same Branner-Hubbard estimate is true. So so now it's due to I don't know, I think it's Favre and Gauthier. So same estimate at p-adic places. And okay, this is true too for a post-critically finite parameter. The p-adic green function is equal to 0. And then as in the quadratic case, you can write down the canonical height. So now the canonical height. So now I must assume that CA is in Q bar here. So of course, I must assume that the parameters are algebraic. So yesterday, I explained that you can always define a canonical height HCA, which satisfies HCA of PCA is 3 times HCA, and which is the bounded distance from the naive height. And using this green function, you can express the canonical height as a sum of local quantities. Okay, and actually, so as before, HCA, you can express it as a formula over all places. So it's the sum over all places over the sum of, so that's H of CA, excuse me. Over all embeddings of what? I'm a little lost here. Of Q of CA into Q into CP of green function evaluated at this parameter. Okay, so don't care about the formula. You just remember that it is a sum of local quantities. It is a sum of local quantities. And if you look at this formula, it certainly satisfies these two assumptions because each of the green functions, all of these local green functions satisfy this formula. And the estimate here is basically this one. Okay, because you only have finitely many places to look at. And on each of these places, you have this estimate. So the formula on the right must define the right. If it's correct, maybe there are some small mistakes in the formula. Okay, so in particular, you have that, you have what? And also, H of CA is equal to 0 if and only if the parameter CA is post-critically finite. Okay, so with all these tools, you can apply the arithmetic equidistribution theorems, which are for points of small height, which are still not stated by my colleagues, but okay, believe in them. So let me state how Nguyen theorems expresses in this setting. So, theorem. Yeah, I think it's Nguyen theorem. Let Zk be a sequence of so I stated for this precise height here of Galois invariant. So Galois invariant. So they are in Q bar square sets such that, so you need two assumptions. The height goes to 0. So height of Zk goes to 0. This height is the average height, 1 over cardinality of Zk sum h of x for x in Zk. So the height must go to 0. And the Zk must be generic in the sense that it escapes every, here we're in dimension 2, so it escapes every curve. So for every hypersurface, there exists some k naught, such that for every k larger than k naught, Zk does not intersect. So over Q bar is empty. Then the conclusion is that this set equidistributes to some measure which is actually the Monge-Ampère measure of the function g. So it is a certain probability measure in space, which is actually the Monge-Ampère measure of this function g. And actually, the parameters CA cube were chosen so that this is a probability measure with our normalization. The square, well, you see that there is no coefficient here. Okay, so the square of this DDC is a probability measure. So I don't want to define exactly what it means, but this is a certain probability measure in space. It is defined using the Bedford-Taylor theory of currents. Okay. So I want to apply this result to post-critically finite maps. So post-critically finite maps are of height 0, so it's not a difficulty here. On the other hand, for sets that I will consider, the genericity assumption is not satisfied in general, and there's a nice corollary. So let me call it 1 and 2. Actually, in the second assumption, you can replace genericity by a weaker assumption. You can replace, 2 can be replaced by a weaker assumption, which is for every hypersurface H, again over Q bar, the cardinality of the intersection of H with ZK compared to the cardinality of ZK goes to 0 as K goes to infinity. So actually, you don't need genericity. You need this weaker assumption. And the proof is a diagonal argument. Let me make the proof. The proof is so what we will do by a diagonal argument, we will construct a generic sequence. We construct a generic sequence of sets, zk prime, which is contained in so it's a sequence, a generic sequence of subset, which is contained in zk, and such that the asymptotic cardinality is the same. So I think it may be a useful remark that in Nguyen theorem, you actually don't need the full force of genericity. Okay, so let me explain how you construct this sequence. So it's elementary, it's just a diagonal argument, but you have to do it properly. So I fix an epsilon positive. I give myself epsilon. And so I will not make the full diagonal argument. I will construct a set zk of epsilon such that, so I will construct, we construct zk prime. So zk prime is generic, and the inf of the cardinality of zk prime over cardinality of zk is bigger than 1 minus epsilon. Okay, and then you have to iterate the process. Okay, let me just do this. Okay, so I have my epsilon positive, and now I enumerate all hypersurfaces. So the set of hypersurfaces is countable, and so enumerate all hypersurfaces. So HL for positive L. So these HL are all hypersurfaces defined over Q bar. Okay, and I will start by studying H1. So let's start at 1. Okay, and I will extract from my. So what I know that. So we know that the cardinality of zk intersected with H1 over cardinality of zk goes to 0. So I'll construct, so you can remove, so for large k, there are very, very few points in H1, right? So for large k, you remove them. And you remove them in this way. So for large k, so you construct, so you wait until, so you wait until this is smaller than epsilon over 4, say. Okay, so for k large enough, so for k larger than k1, this is smaller than epsilon over 4. Okay, so you construct a new sequence zk1, which is zk for k smaller than k1, and which is the point which consists of the points of zk which do not belong to h1 when k is larger. So this is zk minus h1 for k larger than k1. That's a new sequence of points. Okay, and the set of points in h1, this is a Galois invariant set. Okay, so this is a Galois invariant set. And as you see, the cardinality of this set is the proportion is 1 minus epsilon over 4 of the full cardinality. And you iterate this process. Now you look at H2. You look at H2, and you construct. So you wait. So for k bigger than k2, which is bigger than k1, this cardinality here, zk1 intersected with H2 over cardinality of zk1 is bigger than 1 minus epsilon over 8. Okay, because this one is contained in zk. So it has few points in H2. And so you construct a sequence zk2, which is zk1 for k smaller than k1, k2, and which is zk1 minus h2 for k bigger than k2. And as you can see, the cardinality of zk2 for every k, it is bigger. It's less than epsilon over 8 here. It is less than epsilon over 8. And the cardinality of zk2 is bigger than 1 minus epsilon over 4 times 1 minus epsilon over 8 cardinality of zk for every k. And then you iterate the process. You iterate the process. And at the end, what you get is a sequence zk infinity. And when you avoid every hypersurface for large enough k, which avoids such that for every hypersurface HL, there exists KL such that for every k bigger than KL, zk infinity does not intersect HL. So it is a generic sequence. It is a generic sequence. And the cardinality of this zk infinity for every k and the cardinality of zk infinity as compared to the cardinality of zk for every k, this is bigger than the infinite product of 1 over epsilon 4 times 2 to the j. There's a j here, which is, if parameters are well chosen, this is bigger than 1 minus epsilon. Okay? And then you make another diagonal argument to get the zk prime. Okay, so that's a simple observation, but it is useful in this problem. Okay, so now I can state the equidistribution. So it is due to Favre and Gauthier. So actually there were previous versions of equidistribution with a less nice statement. So there are two cases. So I look at the distribution of points like this. PCA of n iterated n naught times of C naught is PCA iterated m naught time of C naught, and PCA n1 C1 is PCA m1 of C1 for some m1 bigger than m1. Okay, so I look at the distribution of such points. And so I don't know if let me call it Z mn, something like that. Okay, and I want to study the distribution of this point z mn. And so there are two settings where this works. So if for every so I give myself I give myself sequences nk mk 1. Sorry, too many indices here. 0 0 k k and n1 k m1 k. So these are the sequence of indices. And I assume, so everything is going to infinity here. No, such that, so assume that either the m's are equals to 0, so m0k equals m1k is equal to 0. So it is the case where the points are periodic. So yesterday in the Mandelbrot set, there were points inside the components. And n1k is different from n0k, and both go to infinity. Or, other setting where it works, you assume that n0k minus m0k goes to infinity, and m0k goes to infinity. And same for m1. So these are two different sets of assumptions, two different sets of pre-periodic parameters. So either they are periodic or they are pre-periodic, and you have these assumptions on the periods. Then the z mk nk are equidistributed. So let me state like this. Dirac mass, normalized Dirac mass at these points, mk nk, converge to the DDCG square. Yes? Same for C1. So same for the index one. Okay, same assumption. Okay? So just remember, so I wanted to state something precise, but just remember that PCF points are equidistributed. Okay? But you need to make small assumptions on these sets. And so if you want to prove this result, so I want to check the assumptions of the corollary of Nguyen theorem. So the point is to check the assumptions of this corollary. So the proof. Okay, so we know that these points are of height 0. So all we have to do is we have to check so the genericity will not be true, but we will check this assumption here. The assumption of the corollary of Nguyen's theorem. Okay, so what is the cardinality of this set ZMN? So Z M naught, so let me state more precisely, N naught M naught, N1 M1. Well, if you look at this equation, if you look at PC, so N is bigger than M in every, so I just look at this formula, PCA N of C. That's a certain polynomial, right, in C and A. And you have to write it down to know what is the degree of the polynomial. So PCA of C, PC of Z, it's Z cubed over 3 minus over 2Z squared plus A cubed. So if you plug in C naught, it means that you plug 0. You get A cubed which is of degree 3. Okay? That's the point of putting a cube here. It is to have degree 3 here in this situation. And you iterate. It's not very complicated to see that when you plug a cube here, well, you will get a term of degree 9 here, and all terms are of lower degree. Okay? So you can iterate PCAN of C0 is the dominating term will be the a to the 3 to the n. So it's a to the 3 to the n plus terms of lower degree. Okay? Now, if you do it for C1, okay, so maybe, so now it implies that the equation PCA N0 of C0 equals PCA N M0 of C0. This is of degree 3 to the n. Not. Okay, and for C1 it's the same. So if you look at PCA of C1, it is PCA of C. It is, so you have C cube minus C cube over 6 plus A cube. So the formula is a little bit more complicated. And when you iterate, so I don't know the general formula, but the degree, so it's the same of PCA N of C, is also 3 to the n, but you see the leading term is slightly more complicated. Okay, but you get certainly, once you have a term to the cube, you plug it here, you get 9, and here is lower. So the leading term is a cube minus c cube over 6 to the 3 to the n minus 1 plus lower degree. Okay, so the equation, the other equation, so PCA N1 of C1 equals PCA M1 of C1 is of degree 3 to the N1. Now, remember that all the solutions to this equation, so when you take the system of equations, everything is compact in C2. Okay, so you have nothing at infinity, so you can count just by Bézout theorem. So by Bézout theorem, it implies the cardinality of this set Z, counting multiplicities of Z N0, M0, N1, M1 with multiplicities is 3, so with multiplicities is 3 to the N0 plus times plus N1. This is because all solutions are isolated, everything is of dimension 0, and there is nothing at infinity because I prove that all the solutions are compactly contained in C2. And actually, these two things are disjoint at infinity. Okay, so now I want to know, so now I take H, a hypersurface, and I want to control the cardinality of H intersected with this set, Z, N0, M0, N1, M1. Okay, I want to show that there are not too many points on this hypersurface. And for this, we have to use dynamical arguments. And this is where the assumptions will enter the story. So the theorem. So we use a dynamical theorem, which is due to Buff and Epstein, and also to Favre and Gauthier, and also Favre and Gauthier. And the theorem says that under these assumptions here, all the intersections, so under the assumptions on the Ni, on the mi and I. All these intersections here are smooth and transverse. So the intersections, the multiplicities, are equal to 1. So all these intersections are smooth, at smooth points of these varieties and transverse. So these varieties, maybe I should give them names. So this one I will call it pair 0 and not m naught, and the same for the other. The pair I and I mi for I equals 0 and 1. They are smooth and transverse. Okay, so this is a dynamical theorem which relies on dynamical arguments. Okay, so you can, by studying the parameter space of cubic polynomials, you can show that these curves under these assumptions, which are maybe not so natural when you don't, I won't give the proof of this. But under these assumptions, all the intersections that you see, they are smooth and transverse. And the proof, so I don't know the proof, by the way. So the proof is based on Teichmüller theory. Okay, so now how can I use this to control this cardinality here? Okay, so if I take a point of my set Z, it means that I have this variety pair 0 and not m naught, and this pair 1 and 1 m1 intersected at a point. And now I pick any hypersurface. So I pick any hypersurface. So perhaps the first remark. So I have to control this cardinality as a set without multiplicity. Okay. First remark: the set of singular points. So we are in dimension 2. So H has only finitely many singular points. Okay. So finitely many of such points are singular for H. Okay, so I only have to look at smooth points of H. And if I have a point of intersection of H and one of this set, it means that H is somewhere here. So it could be transverse to both. For instance, let me use a color here. So we have several possibilities for H. It could be either, I don't know, transverse to both of these curves, or maybe tangent to one of them, or whatever. You have many situations, but in any case, so if this point P belongs to H intersected with pair naught intersected with pair 1, H must be transverse to one of the two. Okay? H must be transverse to either pair naught or pair 1, because both of them are transverse. Okay, so when you want to bound the cardinality of this set, so this implies that the cardinality of the set H intersected with Z, let me write it here. This implies that the cardinality of the set H intersected with Z 0, M naught, M1, N1, well, it is bounded by the cardinality of H intersected with pair 0, N0, M0, plus the cardinality of H intersected with pair 1 of N1, M1. Okay, which is now, again, you use Bezout. Its degree of H bounded by degree of H, 3 to the N0 plus 3 to the N1. Okay, And this is certainly negligible with respect to this one. Okay, so you conclude that the assumption of the corollary is satisfied, and then you have equidistribution. And so from this, you get equidistribution. And that's the end of the proof. Okay. So now we know that the points, special points are Zariski dense and equidistributed. And so now I would like to address the André-Hort problem. And I lost my eraser. So I would like to address the André-Hort, dynamical André-Hort question problem. So which was actually formulated by DeMarco, Baker and DeMarco. So it's not completely obvious to formulate precisely this problem, but the idea is to understand special curves. So the problem is to when, so that's the problem, when can a curve pass through infinitely many special points? Before, I should have said something before. So the theorem that I've just stated on equidistribution is valid in every degree for polynomials of all degrees. On the other hand, it is not known for in the space of rational maps. Okay? So for polynomials, you have nice control of the green functions at infinity, which allow you to apply the equidistribution theorem, because you will show that the height is induced by a semi-positive bundle, which is continuous at infinity. And this information is not known in the space of rational maps. So this equidistribution theorem is known for all degree polynomials. So you have to make some delicate estimates to show that the metric is semi-positive and continuous at infinity. But it is not known for rational maps. OK, so let me come back to André-Hort problem. So when can a curve pass through infinitely many special points? So one possibility, of course, so curve C. One possibility is when C is one of these curves pair not and not M not. So if you take one of these curves, of course, the other critical point will be active on it, and you will create infinitely many parameters where the second critical point is periodic. So that's a possibility. Another possibility is that on this curve, so you have two critical points, but it may be that after one iteration, the two critical points collide. So it may be, for instance, that on C, we have a relation of the form f PCA, P of C naught equals, so PCA of C naught is equal, so persistently equal to PCA to the L of C1. So you have your two critical points, and after a few iterations, they collide, and there's only one critical point. Then, of course, when this image of critical point, which is one single point, pre-periodic, you get a PCF parameter. And you can make it happen infinitely many times. So these kind of curves also contain infinitely many parameters. And if you think a little bit, there are a few exceptions too. OK, and actually, so in the case of cubic polynomials, there is a complete classification. And the answer is that the answer is written here. So let me state the theorem. So a theorem which was actually proven independently by Favre and Gauthier, and also by Ghioca and Ye. So if you take an irreducible curve, so let's C be an irreducible curve in the space of cubic polynomials with critical points marked, containing infinitely many post-critically finite parameters, then there are three cases. So actually the answer is here. Either C is of the form pair n naught m naught of C naught. So no, it's not the right notation. Pair 0 of n, or pair I for I equals 0 or 1. So it is one of these curves. Or there is a collision, a persistent collision, of the form like this: P, K, C, A, C naught equals P, C, A of C1 to the L. So it is clear that if you look at this equation in CA, it's a certain algebraic equation. So it certainly defines a curve in parameter space. So it's not an exception. It's something which happens, and you can just define it. And there is one sporadic case, which is one special curve. It is there is one curve. C is the curve of polynomials. Is the curve of PCA having a certain symmetry, which commute with one special mapping, which is Z goes to minus Z plus C. Okay, so there is a certain curve in the space of polynomials of mappings which have a special symmetry, and well, it happens that on this curve you have infinitely many PCF parameters. Okay, so my initial plan was to give you the ideas of the proof of this result, but so it's complicated, but the ideas are not so difficult to understand. And rather than doing this, which will be too long, I will prove something, a negative case of the conjecture, which is a former result. So let me state another theorem, which is due to Baker and DeMarco. No, I need some notation first. So I will define, so definition, pair. So there is a certain, okay, so the notation will not be completely consistent with this notation here, but of lambda is the curve in parameter space. So sorry, there's a conflict in notation here. I did not think about it. So it is the set of polynomials PCA which have a fixed point of multiplier lambda, having a fixed point of multiplier lambda. And what I want to do is to prove this result by Baker and DeMarco, which is actually implied by this one, but which was proved before. And the result is this one. This curve P1 lambda contains infinitely many post-critically finite parameters if and only if lambda is equal to 0. So you have a family of curves right? It's a kind of pencil of curves, and only one of them is special. So that's the statement. So of course, if you look, this classification here is stronger. So if you look at this classification, you can find this result. But so my idea is to prove, to give a proof of this result here. Okay. So maybe I should make a remark. No, we'll do it later. So yes, let me make this remark. So the result actually is obvious. When the multiplier is between 0 and 1. Because in this case, so in this case, you have an attracting point, and I explained in the first lecture that for an attracting point must attract a critical point. So if you have an attracting point, you will have an attracting point. So it will automatically create a critical point with an infinite orbit. So it attracts C0 or C1, and so either C0 or C1 has infinite orbit. So in that case, this pair 1 lambda intersected with PCF is actually empty. But otherwise, there is no clear dynamical reasons why this intersection should be finite. Okay, so it is interesting when lambda is larger than 1. Okay. So let me first prove the easy implication. So the easy implication is the reverse implication. You must prove that this curve pair 1, 0 contains infinitely many critically finite parameters. So this is not difficult because when you are in pair 1, 0, you already have a fixed you have a fixed point with a multiplier 0. So one critical point is fixed. So it is easy because if P belongs to this curve, one critical point is fixed. And in a sense, the other one is free to move. And the other, so let's say let me be more on an irreducible component of pair 1, 0, one critical point is fixed, and the other one is free. Can move. Okay. Now let's say C0 is fixed, and let's say C1 is moving. Now, is it possible that C1 is passive on the curve? So C1, if C1 is passive along the curve C, then by the theorem which I stated, if it is passive along this algebraic curve, then it must be persistently preperiodic. Then it must be persistently pre-periodic. So that would mean that you would have an algebraic curve where the two critical points have finite orbit. But this is not possible because the PCF maps are points. All components have dimension 0. So this contradicts, say, the boundedness of the special points. So C1 must be active somewhere, must be active along C, And so you can always perturb to make it preperiodic. You can make it preperiodic along an infinite sequence. So this is this Montel argument which I presented yesterday. Okay, so when you have one critical point fixed and the other one free, you can make the second critical point bifurcate, and as soon as it bifurcates, you can find infinite sequence where it is periodic or preperiodic. So you get the answer. So that's the easy implication. So now I have to study the other one, complicated implication, so which will use some arithmetics. And for this, so as I explained at the beginning of the course, one important step, which is not completely obvious, is to find a nice way of parametrizing the curve. Okay, so if you look at the, there is a preliminary step, which is to choose nice coordinates. Because if you look at the original parametrization, so this one, and if you look at this parametrization of polynomials and you try to express the condition that there is a fixed point of multiplier lambda, well, you have a complicated resultant to compute, and you will get a very complicated equation for the curve. So in these coordinates, this curve pair 1 lambda has a complicated equation. And it is not easy to work with. Okay, so I will change coordinates. So what is the general form? What is the general form of polynomials with a fixed point of multiplier lambda? Well, I can always use, so I work up to affine conjugacy. Okay, so I have two parameters in my affine conjugacy, so I can use one parameter to make the fixed point at 0. So under affine conjugacy, you can arrange so that the fixed point is 0. So that the polynomial is of the form lambda z, and the derivative is lambda plus a z cubed plus b a z square plus b z cubed. Okay, and I still have one parameter, so now I can use homothesis to kill one of the parameters a and b. Okay, and actually, so I have one more parameter. So now I use homothesis to kill, well, to play with a and b. And how do I play? Actually, remember what I want to know. I want to work with marked critical points. Okay, so I must be able to compute critical points easily. So if I look at the derivative here, it's lambda plus 2az plus 3bz squared. Okay, and I must be able to solve this equation and follow the solutions holomorphically. Okay, so as you can see, it is certainly better if I can put lambda in front of everything. And let's say 2az. And also, it would be useful if I can write this as 1 plus a certain function of a parameter, one critical point. So, as I said, I must be able to solve this equation and find the two solutions. And so let me give you the formula. So the parameterization that I use is this one. Fs of z is lambda times 1 plus 2s plus 1 over s minus 2 z plus z squared. Excuse me, it's not 2, it's 1/2. And here it's 1, no, z cube here, and 1/3. Okay? If you compute the derivative of this, what you get is this. The derivative is this one. Okay? And now this one, the two solutions are S and 1/s, right? So in this family, so it is a parameterization of this curve pair 1 lambda with both with critical points. Let's call it C plus of S is S, and C minus of S is 1/s. So the two critical points, and it is parameterized by S in C star. Okay, so I have a nice parameterization of my curve pair 1 lambda with both critical points marked, and it turns out that this curve is isomorphic to the punctured plane. Okay, so I will work with this parameterization. Okay, now, and there is a symmetry. Okay, so the situation is symmetric in S and 1/s. As you can see, the equation is completely symmetric with respect to exchanging S and 1/s. Okay, so as before, so I want to use some height technology. So I have to introduce the corresponding green functions. So again, I will study the function g fs of s. Let's call it g plus. And g minus is g fs of 1/s. So these two functions will play a role in the arithmetic equidistribution. So again, it's the green function where you plug the critical points, side. And I have to study these functions and the way, in particular, so think about arithmetic equidistribution. I would like these functions to define continuous semi-positive metrics on a certain line bundle, on P1. Okay? So I need to understand the behavior at infinity. I need to understand the behavior at the punctures. So the punctures are 0 and infinity. So I need to understand how this function extend at 0 and infinity. Okay, so there is a simple observation. If you look at fs of s, look at this formula here, the 1/s disappears. So it is a polynomial in S of the form S cube, 1/3. It is minus 1/6 of S cube plus lower degree terms. And it's a polynomial. Okay? And if you iterate fns of S, it will always be a polynomial because the only problem you can have is with this 1/s here. But since the degree now is bigger than 3, you will always kill the pole. So is a polynomial. It is a polynomial, and the leading coefficient. So you see, you take this coefficient here, and you take the highest degree term, and you iterate. Okay? So the leading coefficient is this one. It will be, so there's a lambda. Sorry, there's a lambda here. So lambda over 3, lambda over 3 to the cube, lambda over 3 to the n minus 2, and minus lambda over 6 to the 3n minus 1, s to the 3s to the n. Okay? Yes. So that's the leading coefficient of my polynomial. So now if I take, so remember, to take the green function, you have to take a log. So the log of this, polynomial here, is something like, let me write down the formula, 1/3 to the n log. It is log of lambda over 6 to the 1/3 plus log lambda over cube to the 1/6 plus log s plus small o of 1. Okay, what does it mean? And so actually what you get that this is converging to G plus, and you get this asymptotic expansion for G plus. So that's the asymptotic expansion for G plus at infinity. And now, so you have two punctures. One puncture. So here, what I'm doing. So remember past lecture, when you have in potential theory, you have a subharmonic function, and you have to know the growth at infinity to understand the capacities of the set and all that. So here, what I'm doing is to give the growth infinity of this function G plus. Now, if I want to look at 0, so in 0 it's easier, because f is a polynomial. So you see that by the maximum principle, for every s less than 1, fsn of s is less than f1n of 1. Okay, just because it is a polynomial. So it implies that G is bounded close to 0. It implies that G plus is bounded near the origin. So it has no pole at 0. So finally, this function G plus, it extends to C, okay, and with this logarithmic growth at infinity, and and it has logarithmic growth at infinity. And by symmetry, it's the opposite for G minus. So G minus has a pole at 0, and it is bounded at infinity. Okay. So one consequence of this consequence the points C plus and C minus, they are not passive along the curve. Because remember that if a critical point is passive along an algebraic curve, then it must be persistently periodic. So the green function is equal to 0. So there must be bifurcations. There must be bifurcations. And also the Laplacian of G plus and the Laplacian of G minus are non-zero. Okay, so now let me apply arithmetic equidistribution. So now I assume, so far I did not assume, I don't make an assumption. So now I assume there are infinitely many post-critically finite parameters on the curve. Okay, so it means that you have infinitely many parameters where C plus has height 0, and infinitely many parameters where C minus has height 0. So you can use equidistribution. So everything is set up so that equidistribution is valid. So first remark. So PCF parameters are defined over Q bar. So the assumption implies that lambda itself belongs to Q bar. Okay, so you really have a curve defined over the algebraic numbers. Now, if you have an infinite sequence, so we have an infinite sequence of parameters Sn such that C plus of Sn is periodic, because we have infinitely many critically finite parameters on the curve. So they equidistribute they equidistribute towards the Laplacian of G plus by equidistribution, right? But also C minus, for the same parameter, C minus is pre-periodic. Okay, so they equidistribute towards the Laplacian of G minus. And notice that since there is a 1 here, the Laplacian is actually a probability measure. Okay, so this is really the Laplacian, not a multiple of the Laplacian. Okay, so the conclusion, Laplacian of G plus is equal to Laplacian of G minus. Okay, so just a small comment here. In all these problems in arithmetic dynamics, we want to classify special objects, like in the Manin-Mumford theorem, dynamical Manin-Mumford, which I have the time to discuss and all that. It is always the same kind of argument. Okay, so you start with a special curve, for instance, and you use equidistribution to get a sort of special symmetry between different objects. So in this case, we have two critical points, and we have this very special. So from the assumption that the curve is special, you get this dynamical conclusion. This conclusion, which comes from arithmetics, and then I will use dynamical arguments to conclude that actually the curve. So here we conclude a contradiction. Okay, so where does the contradiction come from? So the argument is very nice. So in the, I think that this kind of ideas are used in the proof of the Manin-Mumford conjecture by Spiro, Ulmo, and Zhang. Okay, so they use the fact that you have a subvariety with a Zariski-Dense subset of periodic points, and they are able to construct two different height functions and to get a contradiction. Okay, so this is what we have done here. So now we have extracted the information from arithmetic, and now we need a dynamical argument. And the dynamical argument is this one. So from this, we know that G plus minus G minus is a harmonic function. This implies that this function is harmonic on C star. And this C star is the pair 1 lambda curve. Okay, and it is harmonic and it grows. So it is like it grows like log s at infinity, and it grows like log s at 0. Okay, because g minus goes to plus infinity minus log, and so minus g minus grows like this. Okay, so an easy argument from harmonic analysis says that since it is harmonic and it has this growth, it must be equal to the logarithm of s plus some constant. Okay? So in particular, if you look at the set of points where g plus minus g minus is equal to 0, this is contained in a circle. Okay? So now, so conclusion of the argument, so I'm almost done. So saying that these two functions have the same Laplacian, so remember I told you that the Laplacian of G plus, of the green function, is where you have bifurcations. So it implies that the bifurcation locus of C naught is the same as the bifurcation locus of C1. Okay, so these two critical points, they bifurcate exactly at the same place. And this bifurcation locus of C naught, it is also the set of points where G plus is equal to 0. Well, it's the boundary of the set of points where G plus is equal to 0. Okay? And this is the boundary of the set of points where G minus is equal to 0. So what we get from this, we get that the bifurcation locus of the family, which is actually the set of parameters S such that G plus of S is equal to G minus of S is equal to 0, it is contained in a circle. Okay, just because we know the function g plus minus g minus. And that's the conclusion, because there is a theorem which is due to Shishikura and Macmillan, which say that in any holomorphic family of rational maps, the bifurcation locus is a fractal set of dimension 2. Say of any holomorphic, one-dimensional holomorphic family of rational maps. It is a fractal set of Hausdorff dimension equal to 2, which is the Hausdorff dimension of the whole parameter space. So the boundary of the Mandelbrot set has the same dimension as the plane. Okay, it's a complicated fractal set. And so you see that here the conclusion is the bifurcation locus is contained in a circle, which has dimension 1, Hausdorff dimension 1. Okay, and then you get a contradiction. Okay, so this is the contradiction. Okay, so this theorem is the so-called universality of the Mandelbrot set. Each time you take a family of rational maps, when you see a bifurcation, you must see a homeomorphic copy of the Mandelbrot set around. Okay, so certainly the bifurcation locus cannot be contained in a smooth curve. Okay, and that's the end of the proof. Okay, so sorry I could not discuss the dynamical Manin-Mumford problem. Maybe next time. I will stop here.